Lecture 10, Threads. It wasn't that long ago we discussed the concept of what makes a process, and I said that a process has three major components. It has the executable program, it has the data that is created and needed by the program, and the execution context of that program. And we said it is a program in execution, and that creates a process. And a process has at least one thread and can have many. But what's a thread? Well, the term thread is a short form of thread of execution. And a thread of execution requires a definition as well, and that is it is a sequence of executable commands that can be scheduled to run on the CPU. So it is a sequence of instructions, and it can be assigned to run on the CPU. A thread has its own state, and a thread has its own local variables, and most of the programs that you will write in other courses, or at least have up until this point, have only one thread. Your program's code is executed one statement at a time, sequentially in some order, and that's really what we have done up until now, even in this course, that there is a main function. The main function runs for some period of time, and it executes instructions. We've now learned that in order isn't necessarily the order that you wrote things in, because, say, a signal and a signal handler could happen asynchronously, that is, at any time, but we are still doing one thing at a time sequentially, and if you wanted at the end of execution, you could sit down and produce a list that said this is the sequence of steps from top to bottom, from one to finish. This would be an incredibly long list for anything but a trivial program, but it is still possible. When we start to work with threads, that ceases to be the case. A program is multi-threaded if it uses more than one thread, at least some of the time. Obviously, when you start your program, it begins executing with the initial thread, so that's where main is. At the start of main, we start our execution. And then that is our main thread, or the root thread for your process. That thread is allowed to, and frequently will, create additional threads if they are needed. And threads can be created and destroyed as are necessary within the program dynamically. You could also choose for them to be persistent. So you could create a number of threads and keep them around. Those threads hang around to do specific jobs. Or a thread can be created for a specific purpose. We have a write to the database that we want to handle. We can create a thread, give it to that thread, and then that thread will terminate when it has finished the assigned task. In that sense, you can think of threads as being somewhat like child processes. They are created at the request of a caller, in this case a parent process, and they can be persistent, or they can do a specific thing and then terminate, and that is fine. Now, if you want a diagram that shows about threads and processes, here you go, this classic diagram. Up at the top left, that is one process, one thread. That is what you most likely did in your introductory programming course and your data structures and algorithms course, or any other course where you haven't gotten into different threads and different processes. And that's very simple, right? If you're only doing a small thing, then sure, you can do it with one process, one thread, no big deal. The bottom left quadrant is what we have introduced in this course, where we talked about multiple processes, but each process has only one thread. It's only doing one thing at a time, and that is our model for what happens when we have a parent process that creates a child process with fork. The top right corner, the one process, multiple threads approach, is what we're going to learn about today, and the multiple threads approach will come to dominate most of the examples that we will do in this course, and we will probably do much more with threads than with processes. You might still do things with processes. We'll see what is the difference between having multiple threads and having multiple processes, but we'll see. And in a lot of examples that we're going to do, we will just do multiple threads. There is no restriction that says just because you have multiple threads, you cannot have multiple processes, and that is why the bottom right quadrant of the diagram exists. It tells us that there are programs, and we could write one if we wished, that have multiple processes and multiple threads per process, and it's really just a combination of the top right and bottom left versions, in that we are going to learn how to create multiple threads within the same process, and we already know how to create multiple processes, and if you combine them, then you get the bottom right quadrant as the result. Now, in a process that has more than one thread, every thread has some things that belong to it and it alone. It has a thread execution state, so this is like the process state. Are we running right now? Are we ready? Are we blocked? It has some saved context when not running, so we can resume this later. It has a state that is saved and can be restored. And there is an execution stack, and that is the function calls, and the stack local variables will be different in each thread. And number 4 is, of course, local variables. Number 5, all the threads share access to the memory and resources of the process, so any data, any files, any executable code, that's all shared between all of the threads. So a visual representation of that in a single-threaded process, there's one thread. Threads are always represented as these squiggly lines because, I guess, it's like a thread that comes off your shirt or something to that effect. Why not? This is not an art class. That representation of a thread is fine. And the code, data, and files are shared always between all of the threads. But if we look on the multi-threaded process, we'll see there are, in this case, 3 threads. Each thread has its own stack. Each has its own register data. But the code, data, and files are all shared. This does mean, for example, that if any thread opens a file, other threads in that process can also access that file. You can do a read of that file. You don't have to open it a second time from a second thread, and that actually wouldn't even make any sense. And data and code being shared imply that memory is shared between all of the different threads of the process. This is both advantage and disadvantage. Advantage in that it is fast to communicate between threads, but disadvantage means that more coordination will be necessary to actually make that happen. Now, the way that programs are written these days, very few programs are not at least a little bit multi-threaded. And we'll think about that for just a minute and try and think about why this might be the case and how that might be the case. A common way of dividing up the program is to separate the user interface from a time-consuming action. This is especially important when we are looking at a graphical user interface, because basically nobody wants to see the not responding dialog, as shown here. You might be familiar with this problem. But if you considered, say, a file transfer program, if the user interface, where you select the file that you want to upload and the upload method share a thread, once the upload is started, the user can't use the UI anymore because, of course, the thread is busy uploading the file, and in the meantime, it can't respond to the event, even if the event in this sentence is the user has decided they want to cancel the upload. So that's not good. That's a bad user experience. If the user interface is doing a long time-consuming task, you get the not responding thing in the dialog title, you get the spinning beach ball of death in Mac OS. It is not pretty. You don't want that. It's a bad user experience, and for some reason, users hate having bad experiences. So we have 2 ways that we could alleviate this problem. And one is that we could fork a new process. The child process is responsible for doing the upload. Or option 2, we could spawn a new thread. Whichever one we choose of these two options, the newly created entity will handle the upload of the file, and whatever we do, the user interface will remain responsive because the user interface thread is not waiting for the upload to complete. You could imagine if we created a new process, then we're waiting for UI events, and if we observe a cancel, then the parent can just sig kill the child, and, well, that terminates the upload. That was easy. And we can do the same thing with threads. They are also good for this purpose. We will see in some more detail why we choose between threads and processes in just a moment. In the meantime, I'll also point out the example here represents some sort of desktop application where we're doing a desktop operation of uploading a file. But if you've done programming using Android, or I presume it's the same for iOS, although I don't have direct experience with that, that there are certain things that need to be done using tasks. And tasks are run in the background somehow so that you don't actually freeze the application and make the user interface unable to respond to events. And that works on a very similar principle to threads. The difference is in how explicit you are about creating a thread and saying what you want to do. Some of the details of creating the thread and handing out the work are abstracted away in something like a task framework, but this is C, so we're going to do it the hard way. But honestly, it's not too hard, and it's something that you should be quite comfortable with before too long. Okay, but why threads? Why would we choose threads instead of creating a new process? Well, the primary but not the sole motivation is performance. Creating a new thread is about 10 times faster than creating a new process. Creating a process requires a lot more overhead and just requires a lot of resources. If you tried to exhaust the resources of the system by creating new processes, that's doable in a manageable amount of time. If you try to exhaust the resources of the system by creating too many threads, that would take quite a lot longer. So the thread is a much less heavyweight version here of a process. By that same token, terminating and cleaning up a thread is faster than terminating and cleaning up a process, and it takes less time to switch between two threads within the same process than it would to switch between two different processes. That's mostly because less data needs to be saved and restored. In the ancient operating system Solaris, it was made by Sun long ago before they were acquired by Oracle. Switching between processes is about 5 times slower than switching between threads. Number 4, shared memory space means there's no need for inter-process communication. That is, we don't have to use any of the IPC mechanisms that we've talked about. They can just communicate directly using the memory of the process. This is a bigger item than it might actually seem because, well, inter-process communication can be quite expensive, and there is obviously a cost doing something like shared memory setup. And threads are great because, as in the file transfer program or anything to that effect, it really allows us to make our program be responsive in a way that it just otherwise wouldn't be. And responsive in this case can also mean faster versus if we used processes. And if you wanted some scenarios for where you might apply threads, or perhaps you could think of this of how you would apply threads in a program that's running in a general purpose operating system, there are 4 examples that I'm just going to touch on briefly. The first one we already covered. This is foreground and background work, so the ability to keep something happening in the background, upload a file, or do some task, while the user interface in the foreground is still responsive. Number 2 is asynchronous processing. And here's an example that you might be familiar with. Suppose you were editing a document in Microsoft Word, and for whatever reason, Word crashes, or your laptop runs out of battery, or something like that. When you restart, when you open Word up again, Word presents you with a partial document. It says, hey, I found this recovered version of the document. What do you want to do about it? You can open it again. You can discard it, but it probably has saved has saved the day for you at least once in your life, because, well, you forgot to save, and then, it crashed, and how much work was I going to lose? And you will find, actually, that you might lose a little bit of work, but not that much. Why does that happen? Well, to protect against power failure or a crash, your word processor might write the document data to disk periodically in some temporary file. And this is done without really you noticing, most likely. If you pay careful attention, you might actually see at the bottom of the screen it telling you what it's doing. But for the most part, you probably didn't notice this, and this feature helped you, but it didn't ask you, hey, would you like to save right now? You didn't get Clippy saying, saving your work is important. Would you like to save your work? No, Clippy. Don't want to talk to you anymore. And this is asynchronous processing. So without any particular user interaction, just periodically in the background, we're going to save the state of the document into a temporary file so we could recover it if there is a crash. Item 3 in the list, speed of execution. So, in principle, a multi-threaded program can get more work done in the same amount of time. The amount of increase that you could get is somewhat dependent on the nature of the work that you're doing and the hardware that's available to you. But just as the operating system can run a different program when the currently executing process gets blocked for a disk read, for example, if one thread is blocked, another thread may execute. Alternatively, we might have a CPU that has many cores. You might have a quad-core, 8-core CPU, and we could maybe put them all to use by using threads. The fourth common usage of threads is modular structure. So a program that does a bunch of different things can be given a certain kind of structure through the use of threads. In this case, a thread is assigned to a specific job, and then, well, when it's their turn, when there's something for them to do, a thread does its job. You had one job. And this kind of structure is quite common in processing tasks. When you have many stages of something to process, well, you will have workers who do stage 1 and you have workers who do stage 2. And a worker in that case is a thread, and you end up with some sort of assembly line type structure if that helps you visualize it. Okay, but nothing comes for free. There are drawbacks. One is that there is no protection between threads in the same process, so they can, of course, mess with one another's memory and do bad things that were not expected, unless, of course, we do a good job of coordinating. Once we know how to create threads, we're going to spend a great deal of time talking about how to coordinate these things effectively. One of the other things that is a minus is that we have a little bit less fault tolerance. If any thread encounters an error, so there is a segmentation fault or division by 0 or something like that, the whole process could be terminated by the operating system. If instead you split up your program into multiple processes, then if one of them dies as a result of a seg fault, it doesn't take down the other ones. So you will have a little bit more protection, a little bit more safety if you use processes, but you will have more performance if you use threads. The nature of the work that you're doing will help you to decide what it is you want to do. I think it is very likely in most scenarios you will want to use threads, but it's not a blanket statement. It's not a rule that is always true. Now, each individual thread has its own state. And the process model that we discussed earlier had 7 states, and the thread state model is the simpler 5-state model. That provides you with some clarity, I think, onto why we talked about the 5-state model in the first place, as opposed to just being like, well, this is a bad version of the 7-state model, so, forget it. The 5-state model better represents what is actually happening for a thread, because if a process is blocked, we don't really care why, even if the operating system does. And for a thread, it doesn't matter if it's swapped or not swapped or anything like that. It is in one of the 5 states. And transitions in this diagram work the same way as they did for state transitions of a process, and as before, there are not shown transitions to terminated because a thread could die at any time. And in fact, in the example that we started with, a file transfer upload being canceled, that's actually a termination that we should consider. It might be running at that time and proceed to terminate it, or it might be blocked waiting for the network, and that would also be a form of cancellation. It would just go straight to terminated. Right. The term pthread we're going to use a lot, and it refers to this POSIX standard, also known as IEEE 1003.1c, that defines thread behavior in Unix. This is a specification document that says how threads should behave, and this is a huge document. It contains something like 100 function calls, and we will by no means look at all of them. We will look at some of them, and by the time we get to the end of the course, we will have looked at a significant number of functions that are listed in this standard, but we're not going to focus on all of them, and we're going to start with a smaller set, in particular the ones that are shown on the slide. Anyway, the goal of the standard is to make it so that code for one Unix-like system can run easily on another. So you have a program and you're writing it on ECE Ubuntu, that's a Linux system, and you want to run it on FreeBSD, which is a BSD, Berkeley software distribution system. It should, in principle, be possible to make the code that you wrote in Linux run on the FreeBSD system without having to change too much. Maybe not nothing, hopefully nothing, but maybe the changes needed are small. So that's the goal of the standard. And we're going to focus on this list here for right now. We're going to dig into every one of them in some more detail, and then we'll do some examples where we run some of them. But if you just want a brief high-level overview of what these are, pthread create is used to create a new thread. You could think of it as being analogous to fork, but in this case, we don't duplicate the current thread or anything. It just creates a new thread according to the details that we give it. Pthread exit terminates the thread that calls this function. It is like the exit system call in that it ends execution and returns a value. Pthread join waits for a specific thread to exit. This is like wait. The caller cannot proceed until the thread it is waiting for has exited, and you can only join a thread once, and if you try to join a second time, that is an error. Pthread detach. This is used to make it so a thread cannot be joined, and in some cases you actually want that. You are not waiting to collect a result from that thread ever, in which case you can detach it. We'll talk about detach in some more detail later. Pthread yield, included here only for completeness. I don't think we're going to use it in any example, and I don't think it is something that is important right here. But yield says release the CPU and let another thread run. The real purpose why it's here is to illustrate that there's an expectation on the part of the operating system that because all of the threads in the same process belong to this same program, we expect the threads want to cooperate, and they're not trying to compete for CPU time the way that processes do, and therefore it is sometimes correct for threads to make decisions about when it would be better to let somebody else have a turn. There are attributes that are associated with a thread. Attributes are not something we're going to go into a lot of detail on, but they contain details like what is the priority of the thread, after you, sir. Oh no, after you. And you can create an attribute structure, configure the attributes, and use that in creation. And similarly, there is a destroy function for the attribute structure once we're done with it. There is pthread cancel. This sends cancellation to a thread, and we'll learn that there are two kinds of cancellation. And there is pthread test cancel, which is a thread can check to see if it has been canceled, and if that's the case, this function actually terminates the thread that calls it. So either we have not been canceled, and pthread test cancel says, no, you haven't, go on, or if you do pthread test cancel, the current thread dies if it has been canceled. Okay, this gives you sort of a brief overview of the toolkit that we have. Like I said, this is not everything. There will be a bunch more that we're going to talk about, but we will start here, and we'll start to go into some detail about the ones that are important. Pthread create is the first one. It's only logical we should start with creating a new thread. The short version of what pthread create does is it starts a new thread with the attributes that you specify, and it runs whatever function you tell it to run in that new thread with a provided argument. Okay, maybe the short version was long. Maybe that wasn't the clarifying sentence that I hoped that it was. Okay, pthread create takes 4 parameters. So the first one is a pthread t structure. The pthread t struct, like a lot of structures that we've seen, is opaque to us. It is not anything that we know the implementation of. We don't know the internals of. We don't know the details, and that's fine. It is just a handle. It is something that we use to reference this thread if we need it. It will be initialized by pthread create. So we have to allocate, obviously, memory for the pthread t structure, but it will be initialized by pthread create, and then once it's been assigned a value, we will use that pthread t struct to refer to this thread later so that we can do other operations like join or cancel or something like that. The second parameter is a pointer to the attribute structure, which is of type pthread attrt. This, again, allows you to configure various characteristics of the threads, but you may supply null if you are satisfied with the defaults. In this course, we will be satisfied with the defaults. A more advanced usage, if you cover threads again in a future course, might consider the concept of using the attributes to make your thread behave in a certain way or have certain properties, but that's fine. The third parameter is a function pointer, and this is the function that a new thread is supposed to run. This is not the first time we have encountered function pointers. We saw them actually with signals, and we saw them again with curl, but I would understand if you didn't feel 100% comfortable with them because they are sort of syntactically a little bit strange and perhaps somewhat new. But start routine is the function that the new thread is supposed to run. And you may name this function anything you want. What is important is that it has void star return type, and it takes one argument of type void star. The last argument in this arg is, well, the argument that is passed to the start routine when you run it. So that part is straightforward, I hope. Again, analogous to what happens with curl. When you set up a callback, you set up, this is the callback function. Let's say it's a write callback, and then you also set an argument, and that argument will be set in the callback when the callback runs. Okay. So the type of start routine is this function signature, and you call pthread create with the name of a function matching that signature, and here is an example of what I'm going to do when I want to invoke this pthread create function. So I have somewhere a definition, this function do something, it matches the signature as is required, it has a void star return type, and it has one void star argument. And after creating a new thread, so after pthread create has run, there will be 2 threads in it. There is the main thread that goes on to whatever statement immediately follows from pthread create, and then the new thread that is created will start at the beginning of the function do something. Scheduling of those threads, much like scheduling of the processes, is left entirely up to the operating system. The operating system gives you no guarantee about which thread will be executing once the new one is created, and it could be either of those, the original thread or the new one, or it could be a different one entirely. We don't get to decide that. There can be only one. In C, it's normal to have a single return value from a function, but usually we can have a lot of input parameters. And in C, one of the ways that we get around the limitation of having only one return value is we say, oh, well, we want pointers for the arguments, and we'll just change the things that are passed in, which makes functional programmers very sad because, and even makes other programmers very sad because changing things at random, has unexpected side effects and is bad for your program's structure. But here we only get one of each. There's only one input parameter and there's only one output parameter. Well, what do you do if you want to pass multiple arguments? Don't say put them all in global variables. That might happen in an exam question if you're writing the exam question by hand, because, well, there's only so much time, and it's just eliminating some of the, I'll call it grunt work, that you would have to do. And what you actually should do, of course, is define a structure for your arguments and for your return types. So you've defined a struct, parameters t. It has as many fields as you want, as much data as you want, and then you just, inside the function that's going to run in the thread, just cast the pointer here. So parameters t star arguments is assigned, and then the cast of args, and then you can continue after that. You probably were going to have to cast it anyway, so no big deal. The solution to that, to the limitation of having a parameters type, again, is a bunch of grunt work because you have to define this struct and you have to pack it and maybe unpack it on the other side. And that's okay, and like I say, that's not something that, at least on a handwritten exam, I would want you to do, just because it wastes your time writing things by hand that aren't the focus of whatever question you're being asked. When you're doing it on the computer, and first of all you can type it and you've got the compiler at hand, it's not nearly as painful, so it does make more sense to pass arguments using a struct that way. It is important to note that there is an expectation that the caller of pthread create has to know what kind of argument is being expected, and you write it accordingly. So you write the call to pthread create such that the last argument is a match to what is expected by the function. That's the same thing with the callbacks that we saw in curl, that the compiler can't really help you out here if it's void star this and void star that. It won't know that, well, we were expecting that function do something expects a parameters t, but we actually provided an arguments t. That can't be caught for you by the compiler, so we do have to be careful, and we do have to know what to expect. This is not unreasonable. Again, we're talking about code that's running within the same program, within the same process, so it should be possible for you to just look at the implementation and figure out, all right, I know what I am supposed to do here. About attributes. I'll just tell you what attributes are for completeness sake, but we're not going to use them, I don't think, in anything in this course. But attributes can be used to set whether a thread is detached or joinable. You can set scheduling policy, you can set stack size, you can set all kinds of stuff that isn't particularly relevant for us. By default, though, new threads are joinable. That is to say, some other thread can call pthread join on them, and you can prevent that by creating a thread in the detached state or using pthread detach. There are two properties about threads that are interesting to us. One is whether a thread is joinable, and there's another one about its cancellation type. But you could configure those using the attribute structure, but we won't. There are other functions to do that, and we will use those other functions. So you can use null for the attributes when you're creating the thread, and that gives us the defaults. You can override the one or two things that are necessary if that occurs. I'll point out that there is no mandatory hierarchy of threads. Any thread can create any other thread. This is not a power that is restricted to the initial thread or the main thread of your program. Any thread is capable of creating other threads, and that's allowed. There's nothing wrong with that. So just keep it in mind, there's no necessarily hierarchy. All right, so off we go. The newly created thread is running, and it executes whatever function we told it to run, and that includes whatever function calls it makes until we get to the end. You can terminate your thread with pthread exit. A return statement at the end of whatever start function was provided also has the same effect. But that's not the only way to terminate a thread. They can also die unceremoniously, but probably you don't want that. Pthread exit or return is fine, and sometimes you want the thread to hang around. It should never exit. It takes work out of the queue, does some work, and writes it to a file. Well, it doesn't need to return a value, so we can just kind of let it live. But if the goal is to get a return value from the thread, then we need it to exit. If a thread has no return values, it can just return null. This sends null back to the thread that has joined it. And if a function that is called returns normally instead of calling the exit routine, just uses a return statement instead of pthread exit, the thread is still terminated and the value is returned. So there isn't a hard rule that you have to use the pthread exit function. I'll also point out, if I haven't mentioned this earlier, that null in C is equivalent to a 0, and it is not distinct from 0. If your programming experience is in something like Java, you might think, oh, well, I can use null as some sort of sentinel value in an array, but you kind of can't because it means the same as 0. Okay. Now, another way that the thread might terminate is if, well, it gets canceled using pthread cancel, which we're going to come back to in a little bit. A thread can be terminated indirectly, and if the entire process is terminated for some reason, again, if there's a division by 0 or something like that, that will actually terminate the entire process and it kills all of the threads. And also, if main finishes, when you get to the return 0 at the end of main, that kills all the threads in the process as well. However, you can prevent that from happening by ending main with a call to pthread exit, and that will automatically wait for all of the threads it has spawned to exit before main is finished, meaning that threads that are not quite done will be given the chance to finish. All right, report number 1. Like the wait system call, the pthread join call is how we get a value from a spawn thread, and pthread join takes 2 arguments, pthread t thread and void double star ret val. I want to point something out here now, that thread here is pthread t no star. That's not a typing error. If we go back to pthread create is pthread t star thread. Also not a typing error. The API specification for pthreads is a little bit inconsistent. There are some functions where expected is a pointer to the pthread t struct. There are some functions where what is expected is the pthread t struct itself. So you do have to be quite careful about this. That's, again, just inconsistent, so it makes sense to check those kinds of things when you're writing your code. If the compiler gets to take a look at the code, it will tell you, hey, I found pthread t, and I was expecting pthread t pointer. Are you sure this is correct? And that makes it a little bit easier. If you are not working with the benefit of the compiler, then you should be quite careful and make sure that you check the specification, check the documents, and it will tell you this is what you need to know. For handwritten exams, there's a reference sheet. The reference sheet has all the function specifications on it, and I would always tell people you should look at that, double check, even if you are quite sure that this is pthread join takes a star or it doesn't. You should check, because you'll feel silly if you lose a mark over something like that. Now, the first argument is straightforward, is the pthread t struct of the thread that you wish to join. That is the one that you want to wait for and collect the return value from. And the pthread t struct is, as I say, initialized by pthread create, and if you need it, you can hang on to it to use in a function like pthread join. And retval takes 2 stars. What we are looking for is a pointer to a void pointer. And typically, to get around that, is we are supplying the address of a pointer, and the example will perhaps make that a little bit clearer. So let's look at this quick example of collecting a return value, but actually what I'd like to do is look at it over in the editor, because we can see the syntax highlighting and play around with it a little bit more. So this simple example will introduce us to the idea of creating and joining a thread, as well as using pthread exit. It is by no means exhaustive of all of the things that are worth talking about when we talk about threads, because there are lots more functions that we have not yet covered, including things like detaching and cancellation, what have you. But it gives you a first introduction to the topic. So let's begin. Here on line 3, we have to include the pthread.h header, and we'll see when we want to compile this that you have to provide a pthread argument to GCC. I've defined a function here, run, which is going to be our function that we're going to use for the new thread that is created. So we'll start down here at main. So main checks the count of arguments, and if it's invalid, we exit. Fine. We declare a pthread t struct t, and we have a void pointer here, vr, and we will then create a new thread. And creating a new thread here, we create it using the pthread t struct, but we need a pointer to it, so ampersand t. Null default attributes. The function that we want to execute is called run, and the provided argument here is argv at array index 1. So because a void star is expected, any sort of pointer is valid to provide here as the argument, and therefore pointing in this char star is perfectly fine. There's no need to cast it. That is not necessary. Then we're going to pthread join. And pthread join is a blocking call. It prevents main from advancing any further until such time as the thread that is the first argument, in this case t, has exited, and we're going to provide the address of this pointer, void star vr. vr is not initialized to anything, and it's not no memory has been allocated for it, other than the VR itself that's on the stack. We didn't call malloc on it. Why? Because pthread join just updates the value of that pointer, and that's really all that we need. It will then be pointing to a return value. We will then cast r here to cast vr to r, treat it as an int star pointer. We'll use it in this printf statement, and then we will deallocate vr. I remind you that at line 23, this is an assignment. It's not a memory allocation. It's not a copy or anything. So both r and vr are pointing to the same memory location. So we have to free it once and only once. And pthread exit here is shown at the end of main in place of the return 0. It doesn't matter in this case because we're joining the only thread that we create, and there won't be any that are still executing by the time that we get here. But it is just shown as an example of how to do that. As for the run function, we cast the provided argument, and then we can print it out and say the provided argument is this. And then we allocate some memory here for the return value. We assign the value to be 99, and then we pthread exit, which takes a pointer to that. It's again, pthread exit takes a void star pointer, so we take a pointer to the memory that we have allocated here. Okay, this highlights also a couple of things that are noteworthy about memory allocation generally in a multi-threaded program, and it is that there is no rule that says a thread that allocates memory has to be the one to deallocate it. That's not what happens here. In fact, memory is allocated here in the run function, and that memory is deallocated in main. It doesn't matter really who deallocates the memory as long as somebody does when we know that we are finished with it. And that's the behavior that we observe here, is that memory is used to pass data between the two functions, between run and main, and that's fine as long as we're sure that the memory does eventually get deallocated. So let's compile and run this. And then we can run it. Okay, so provided argument is hello, the other thread returned 99, as we would expect. Now, it is important to note that the return value here has to be heap allocated. We have to declare it int star return val as malloc size of int, and then assign star return val as 99. It is not okay to just say int return val is 99 and then pthread exit with address of return val. Why? Because if it's a stack allocated variable, it goes out of scope when the run function stops running. The run function stops running when we call pthread exit, so it would not be valid for that integer to be used anywhere else. So we should be very careful about this. Anytime we are passing data between two threads, we should take care that it is done using heap memory instead of stack memory, because stack memory could go out of scope and we would not get correct behavior consistently. Okay, another thing that is sort of worth talking about when it comes to working with something like pthread join and what have you is, can you take some shortcuts to do less casting? So let's imagine instead of saying that this is going to be void star return type here, I want to save some time and just do this. In which I replace the VR variable. It's now int star, and we don't need to cast it or anything like that, and we will just attempt to use it as it is. Thing is, this results in a warning. It says passing argument to of pthread join from incompatible pointer type because expected was void double star and provided was int double star. Can we still run the program? Yes. Does it do what we expect? Sorry if I remember to provide the second argument. It does. It is a warning. It doesn't prevent the compilation. Warnings are not good, and you shouldn't just casually ignore them, but you can, if you wish, do this kind of thing where you choose to make it not quite clean in terms of warnings, in favor of making the code a little bit more compact. Can we do the same thing here with the function for run? So instead of having a cast here, we just make the function signature this instead, where it's char star a directly. Can we do that? Once again, we get a warning, and the warning in this case is not on the definition of the function. The warning is on pthread create, and it says, well, the run argument, the third argument to pthread create that you provided, is not quite the same as what I was expecting. It said, well, I was expecting a function that is void star return type with one void star argument, and we actually got was a void star return type and a char star argument. Again, it's only a warning. It didn't prevent compilation. So can I run this? Yes. Does it work? Also yes. In a lot of the examples that we will do, the code that I write has the extra cast steps and things in it so that there aren't any warnings and everything works cleanly. But if your program is going to run correctly, even though you have got these warnings where it says, well, I was expecting this, whereas it was supposed to be that, it's not bad. It's not a problem. But you might not like it. You might not like seeing all of those warnings, and you might prefer to avoid them, as I do, by giving the extra steps there where there's extra casting to make it a little bit neater, a little bit cleaner when compiling, at the cost of there's a little bit more explicit code that we have to read. One of the other things that I will show is the use of pthread join when we are not interested in collecting a return value, I will open up a second version of this, which is functionally identical to the first. And in this case, instead of pthread exit here with, instead of creating the return value and all that, we'll just delete that. And we will have another printf statement here that says, our is 99. And then return null will be effective here. We could also incidentally, if we wanted, just quite simply leave that statement off. If you leave that off and you get to the end of the run function, the compiler is kind enough to fill in for you, oh, okay, you mean return null at the end of that. And if I'm not interested in collecting any return value, then the second argument to pthread join is simply null. And then, of course, there's no value to provide here, so we will delete this and we will say the other thread returned nothing. Factually correct, the best kind of correct. And then we can compile this and go. No, output is pthread 2. And again, I have to provide an argument. And our value is 99. The other thread returned nothing as expected. And just for completeness, I'll demonstrate the fact that if you just leave off the return value here in run, nothing bad happens because the compiler will work it out for you. And no issue there. Okay, so as we saw, the pthread join is, in this case, just a mechanism of coordinating. It's just a way of making sure that the other thread, the one that runs function run, has finished before we go on to the next statement. So in that sense, it is like a wait where we're disinterested in the result. We simply ignore whatever it is. If a value is returned, and you can return a value in run, but if pthread join is called with the second argument of null, it says, we don't care, throw it away. And in that case, pthread join is just a mechanism of coordinating, making sure that that thread has finished before main is allowed to proceed any further than that. Now, it's also noteworthy that there's no requirement, incidentally, that create is immediately followed by join. In fact, in most cases, you don't want that. In most cases, you want to do some useful work in main, maybe create more threads, or maybe do something else in the meantime, and we'll only join the threads later. But in this very simple example, we have create followed immediately by join. So that, again, gives us a quick overview of how we use pthread create and how we use the join function to coordinate with it, and also a little bit about pthread exit. For one more example, incidentally, we can delete this provided argument here if we're not going to use it. And if that is the case, then for the last argument here, we can simply provide null, in which case nothing is passed as an argument here. A would just point to null, and there's no reason why you would use it for anything. You might find, incidentally, if you look at some previous code examples or exam questions, if you're not going to use the value that is provided here to whatever function it is, I sometimes name the variable ignore, just as a hint that you're not going to need it, it doesn't do anything, don't use it, and then you don't have to cast it to anything, and you just provide null as the last argument for pthread create. And of course, in this case, it says our value is 99, the other thread returned nothing, as is expected, because we no longer used that value of argv at index 1. So when we pick up this topic again, next time we will be continuing with the discussion about threads. There were more functions that we didn't cover, in particular things like cancellation, and so if you are ready for that, I will see you at the next video.